Hi everyone. So I'm here to present a task for next year. It's called Eyes and Ears Together. So I'm Yasufumi Moriya from Dublin City University. I'm working with Gareth, and we have some help from Florian and Ramon from Carnegie Mellon University. So the first, we just had a speech processing without audio, but we go to the opposite direction. We have a multimodal speech recognition and processing, so integration of visual features into speech processing system. That's the core idea. So I'm going to introduce a motivation for that. So human language understanding is a multimodal process. For example, the bottom left figure, this is a psychology experiment, and participants are presented with this figure, and they hear the sentence, put the apple on the towel. And at this point, people are looking at the towel, the other towel, but actually the full sentence is put the apple on the towel in the box. So they predict a sentence based on this visual figure, and this is one contextual information. Another example is a famous McGurk effect. So this man is making a sound da, da, but the video is showing a guy closing his mouth and pronouncing as if he was saying ba. And people hear ba rather than da, although it's actually the sounds in the audio file. So that's a motivation for human speech perception. And also there is a practical motivation as well. So automatic speech recognition system is performing poorly for the multimedia dataset. There are some previous experiments. People worked on YouTube data or BBC TV shows, and error rate was very high, 30 to 40%. Why it's very hard? Because user-generated content normally has a less controlled recording situation. So there is a background noise, or a microphone is far from the speakers. Also, topics are mixed. Everything is mixed together, so it's harder to correctly recognize the such data. Actually, integration of visual features into automatic speech recognition. This is not a brand new idea. There has been audio-visual speech recognition. The idea is motivated by McGurk effect, which I showed right before. But this one has a limitation. So to use a lip feature, a speaker has to talk to a camera all the time. And this never happens in a real-world scenario. We want to handle this kind of open domain video where a speaker is not looking at the camera all the time. We have a dataset. This dataset was created in Carnegie Mellon University. This dataset is a collection of instruction videos. It contains video, audio, transcription, and various kinds of metadata. So here is an example. This man is teaching how to play golf to viewers. Okay. This is our baseline system, or how to fuse visual information or contextual information to automatic speech recognition. So we have here a video frame extracting a fixed length vector with a convolution neural network. And we have two, in speech recognition, there are two components. One is an acoustic model, which predicts probability of sound given audio frame. To adapt acoustic model with image information, we just concatenate with audio features and visual features. These are just a vector and provide it to acoustic model. We can also adapt a language model with LSTM. In this case, we feed visual features as the first token, and then followed by embedding words. Then we can get the probability of words. So this is one of the experiments. This is an experiment conducted by the CMU group. So they have tried object features and scene features. Both are from a convolutional neural network. This could be extended to end-to-end. So one neural network and audio input and output is words. This is also possible. That one is in this 2018 paper. They had a reasonable reduction in word error rate, both in acoustic model and language model adaptation. The interesting thing was acoustic model adaptation was more effective when the speaker was outside the building, so in more noisy conditions. For example, this woman is talking on the bus, and word error rate reduction was nearly 6%, which is impressive. This man also talks in front of the airplane, so reduction same near roughly 6%, which is very good. This is the experiment we have done. It's going to be in a spoken language technology workshop this year. We have embedded a video title. So as I talked, this data set is accompanied by metadata, and there are video titles available. So what we have done is this is an example video title, fashion design for small colors and something. And we have extracted word embedding from each title word, averaged together, and we consider this as a video title representation. And that worked reasonably well. We only adapted LSTM language model because we didn't think that video title representation is useful for audio adaptation. Maybe it is, but I'm not sure about that. There was a reduction in perplexity, 5 points, which is good. Word error rate is also 0.3, not much reduction. But interesting thing was, so this is one utterance example, and the green line is a probability of a word to predict. So pan and the color. The adapted model with video title information gave higher probabilities to these words because these are keywords in this video. Whereas the blue line, this is a baseline model without adaptation, and it gave less probabilities to these keywords. So that was interesting to take. So here is the task proposal. We can first run standard AVSR task with multimodal information. We are interested in what kind of visual features or contextual features, such as video titles, can help reduce word error rate. And also, the architecture was pretty simple in the previous example, but maybe we could explore more better approach to integrating contextual information. Another interesting task is multimodal co-reference resolution. So this is a paper from Kwang et al. In 2018. So they have cooking data with video and audio transcription. The transcription is simplified. So here they only have an imperative form, and now cut it with a knife. But in their approach, they can link this "it" to the tomato in the figure, also the knife to the object knife present in the video. So we might be able to run this task as well. It will be interesting if we have this co-reference resolution system to improve AVSR as well. There are many possibilities for that. Yeah, that's all from me, and here is a list of references. Thank you.